The next topic that we are covering is stresses on other planes. This is a new topic, but it's going to be related to beams. So, we're still not quite off of beams. But what we have found at this point, I want to review what we found and what it means, and then what we are going to get to here. So what we have done at this point is that we can compute sigma and tau for any point of interest on this beam. So I have this beam here, and if I ask you, I can pick any point of interest anywhere on this beam here, all over the place. I give you the point of interest. You can give me the sigma and tau for any of those points of interest. So let's just consider for a moment this point of interest right there, and I'm going to draw it as a very small square. Okay, so we're going to be drawing these squares throughout this topic matter that's going to go on for several lectures. And you have to remember that that square is really a point. So it's tiny. I can't, obviously it's meaningless for me to draw a really tiny square because you can't see it. So I have to make the square bigger, but do not forget that when I draw a square, it is actually a point. Very small square. As in other words, I draw a big square, you think, okay, it's really a small square that could be located, anywhere on this beam. So, okay, so that is the first thing you got to remember that is easy to forget as we get more and more into this whole process. And so we can get the sigma and tau, and then we can draw them on this square. So this is my square here, my square there, and I'm going to draw the sigma and taus that we calculated on that little square. And like I say, we will make the square look big so we can see the stresses. So I have to draw it bigger than it is. It's really meant to be tiny. So suppose I have this beam here, and suppose I load it with, point load at the middle, that sort of thing. And just to let you know, envision this being a concrete beam, for instance, where you know from your materials class that concrete is very weak in tension. And so what does that mean? That concrete cracks in tension easily. Now, if I load this beam too hard, what's going to happen to it? Well, I'm going to get cracks. And one of the purposes of this particular topic that we're covering right now is, well, we're going to learn something. We can predict the orientation of those cracks, for instance, and that's something that we get out of the analysis that we're going to do. Okay, so here is my point of interest that I'm going to use, and I'm going to make a cut right there, and we're going to analyze this essentially. So here's my free body diagram of the cut as we normally do it. We've got our AY, and we've got our V, N, and M there. And if I look at this little square, and that's the square here, what do I find? I can compute my sigmas and my taus. So I'm going to get my sigma and my tau, and what do I know? I know that sigma is equal to minus my over I. And in this particular case, as you can see, I've drawn this above the neutral axis, which means that it is in compression. So here's my compression. So sigma is equal to minus 1 it's the same over here. They have to be the same to keep this in equilibrium. So the two sigmas for this tiny little square are equal. So I have, now, how about my tau? Well, my tau is VQ over IB. So there's my tau. And this is the same thing over here, but it's got to go the other way to keep it in equilibrium. So, and it makes sense if you reason out, the laminations and things like that I have a tau going one way up there, I've got the tau going, same value, same VQ over IB, but it goes in the other direction there. Now, so as I've done this, what have I seen? I've got this stress and this stress. I've got this stress and this stress. Well, considering those stresses, if I were to take, for instance, moments about this center of this tiny square, what would happen? Well, notice that this goes, sort of creates a moment like that, and this creates a moment like that, which means that I have a clockwise rotation about this center here for that. And in other words, it's not in equilibrium. So to get equilibrium, what do I need? I need this and this here to cause a counterclockwise rotation, and it's got to be equal and opposite to the clockwise rotation. And so this value is VQ over IB, and this is VQ over IB. So on this square, we have been able to figure out, the sigma here, the tau here, and the tau here on this little square. Now, notice that we've been talking about planes. In other words, this plane here, the sigma is perpendicular to that plane. That's how we get the normal stress. And it's this plane here, it's perpendicular to that plane there. And this is a horizontal plane, and this is parallel to the horizontal. This is a horizontal plane, it's parallel to the horizontal plane. So, in other words, the planes that we have been looking at, that we have been able to figure out these stresses, the sigmas and the taus, have been vertical planes and horizontal planes. And that's it. Vertical and horizontal planes. But now, for instance, maybe I want to know, what are the stresses on this plane? How can I get the stresses on that plane right there? That is the topic that we're working on. So that's what we're going to answer here. Now, that's an example of one at 45 degrees, but maybe I want the stresses on a plane here, or a plane, or this plane, or that plane, or that plane. This technique that we're going to develop will get the stresses on any of those planes, and that is what we want to compute. So, okay. So, for instance, suppose we want to know the stresses on a 45-degree plane. How do we do that? And so the purpose of the next couple weeks is to answer this question, for any angle. What we're going to do is we're going to consider the general case. So in other words, here we're analyzing a beam. We're looking at one point on a beam, but that's because we're analyzing beams in this class. The technique that we're going to develop will be, for instance, we're also going to look at pipes, and we're going to look at pressurized spheres and tanks, and so there are lots of different, an airplane wing, or whatever, everything, columns and structures of all sorts we can analyze. And in other words, if I'm analyzing a pipe, I don't get sigma is equal to minus my over I. I get a different equation. I don't get tau is equal to VQ over IB. I get a different equation. So when we look at different types of structures, we're going to have different equations for our sigmas, different planes on which they act, and our goal will be to, so that's one analysis, and we can do that, and we will do a little bit of that. But in each case, we're going to end up with answers on various planes, but then to get a full analysis, we really need the answer on many planes. So we are going to look at the general case that can be used on any structure. It can be used on pipes and tanks and all sorts of different structures. So in the general case, we're going to have a sigma and a tau on each plane. So I've got sigma and tau on each plane. So if you notice, on this plane, I've got sigma and tau. On this plane, I've got sigma and tau. On this plane, I've got sigma and tau. And on this plane, I've got sigma and tau. So each plane has sigma and tau. And notice there's redundant information on this sketch because this sigma is the same as that sigma. And that sigma is the same as that sigma, and then this tau xy is everywhere here. So in reality, there are really only three pieces of information on this particular drawing. It's the sigma x, the sigma y, and the tau xy. So lots of things are shown on this diagram, and it looks a little bit confusing, but there's really only three pieces of information. But this is the way everybody draws it. So I'm going to stick with the way everybody does this. Now, and put it this way, we're assuming that we know the values of sigma and tau. So in other words, I know sigma is minus my over I, the tau is VQ over IB. So I know these are given information. So we know all of these. I'm showing them as symbols, but we know their numerical values simply because we can do the calculations before we have to do the calculations on them basically before we can go into doing this. So I know the sigmas and the taus. And then I'm going to specify some angle theta on which I want to know the stresses. So I also know the theta. So we know sigma x, sigma y, tau xy, and our desired theta. So those are all the things that we know. What I'm going to do now is I'm going to make a cut. So here's my free body diagram basically. I make a cut right there. I'm going to analyze this triangle. Now, when I make a cut, what happens? Well, I have to put a force or forces. In this case, we're going to put stresses to represent those forces, but that's fine. Now, I don't know what the stresses are on this plane. In other words, I know that there is sigma and tau, but I don't know what they are, so I'm going to specify them as sigma theta and tau theta. And so those are our unknowns. So we do not know the values of sigma theta and tau theta, and our goal is to calculate them. So that's what we're going to do. So there's a little derivation. I'm going to go through this. Okay, so the first thing I'm going to do is I'm going to rotate the diagram. So in other words, we have our triangle, right triangle normally looking like that, but I'm going to rotate it now to make my math a little bit simpler. Like that. So I have my sigma theta and my tau theta are vertical and horizontal now. So that's what I want. Okay, so I'm going to define this is a distance L, and if that is the distance L, then this distance here is L sine theta, and this distance here is L cosine theta. And what I'm going to do is I'm going to take one unit perpendicular to the page here, to the screen or whatever you're looking at, and I'm going to take equilibrium with forces. Now again, we always do equilibrium with forces and not stresses, and I have to convert stresses to the forces using stress times area equals force. So the stresses are constant, so I can use stress times area equals force. If I take one unit perpendicular to the page, then the area over which sigma theta acts is what? It's L times 1 perpendicular to the page. So sigma theta times L times 1 is the force. So sigma theta times L times 1, and then this one is going to be tau theta times L times 1 because the tau acts over the same area. This is L sine theta, so I get sigma y times L sine theta times 1, and tau xy times L sine theta times 1 for that one. And this is L cosine theta, so this is going to be sigma x L cosine theta times 1, and this is going to be tau xy L cosine theta times 1. The xy doesn't really, don't get confused by the xy, it's just the way everybody puts the subscript for this. Okay, so I now have this in forces. So I started out with stresses, and now I've got forces. Now I can do equilibrium. So I'm not going to dwell on this because you can all do this. I'm going to create this coordinate system n and t, and I'm going to take the sum of the forces in the t direction equals 0. I'm going to take the sum of the forces in the n direction equals 0, and I don't want to get hung up on the geometry or anything like that, but so in the t direction, so in the t direction, just start one at a time. That is in the t direction. Then I'm going to have a component of this in the t direction, and this one I've drawn the angle, so that's the easiest one. So in the t direction, what is it? That's going to be the component is going to be times the cosine of theta, so it's, sigma y L sine theta cosine theta, so that's this term right here. And so you need to take components and draw the angles. I'm not going to go through it, but we end up with this equation for the sum of the forces in the t direction. So please look at that and feel comfortable with the angles. The angles are the only hard part. Make sure you get the angles right. And we can do the same thing for the n direction. So same thing, in other words, this is downward in the n direction, and so that's going to be minus sigma theta times L. And then this is the other one I've drawn the angle, so that's going to be downward, so it's going to be minus sigma y L sine theta times the component in the n direction is sine theta, so it's going to be minus so it's going to be minus sigma y L sine theta. There should be a minus sign there. So let me just put that in there. Oops. So there should be a minus there. But minus, oops. Let's make it dark so we don't miss it. Minus sigma 1. All right, so we now have, let's look at what we have here. We have two equations, and what are my unknowns? Well, I only have two unknowns. My two unknowns are sigma theta and tau theta. I know everything else. I know the theta, the L's cancel out. So the L's cancel, so L is not an issue. So the L's disappear with all these terms. So go ahead and cancel out all the L's. And we know sigma y, we know sigma x, we know tau xy. The only thing we don't know are sigma theta and tau theta. So we can solve these equations. Now, the way that it's solved typically is to, I'm not going to go through this using algebra and trigonometry. If you work hard enough in some trig identities, you can get down to this expression here. You can take those two and come down to this expression. And let's look at what this is. So sigma theta minus sigma x plus sigma y over 2 quantity squared plus tau theta squared is equal to sigma x minus sigma y over 2 quantity squared plus tau xy squared. So, okay, notice, here's what, what do we know and what do we don't know? We know the entire right side, right? Because we know sigma x, sigma y, and tau xy. So that's going to be for a real problem, is going to be a number. We know this because that, again, we know sigma x and sigma y, so we know that as well. So this is our solution equation, and it works for all theta. Now, how do we use it? So let's look at what we have here. If we can plot this, what we're going to find is we can plot it. And we're going to plot it in such a way that our x-axis is going to be sigma theta. Our y-axis is going to be tau theta. And so what we're going to get is an xy plot. And so I'm going to substitute in this expression. I'm going to put in x for that. I'm going to put in y for that. See what we have. Well, this equation then becomes, x minus something. Let's take a look at it. X minus something quantity squared plus y squared equals something. So if you remember your high school trigonometry, what did we have? And what did you see before? You had x minus a constant squared plus y squared equals a constant. Well, what is that? What does that plot look like? Well, it's a circle. Because if you remember, the equation for a circle is x minus a quantity squared plus y minus b quantity squared equals r squared. So that is the form of a circle. And note, if you remember, the center of that circle was a comma b, and the radius was the square root of the right side. So we have the same logic for our equation. So for our equation, we have the center is going to be what? A, B. Well, B is 0, and A is sigma x plus sigma y over 2. So that is my center. The radius is the square root of the right side. Now, this is a very convenient way to solve this, and we're going to see why. Not only convenient, it's going to be very simple to get a visual solution, and things are going to pop out at you. So it's sort of like our shear and bending moment diagrams, which, those are great because you can look at the diagram and you see things immediately. The same thing with the Mohr, this is called the Mohr's circle. So this circle has a special name. So the circle that we get with that equation is called the Mohr's circle. And like I say, once we see it, we go, I can see things right away from the diagram and from the Mohr circle plot, and we're going to learn something from it. Now, we're going to have a sign convention. I'm just going to say what the sign convention is. Again, tension is positive, and I'm going to describe what we call a counterclockwise tau is positive. So I'll describe that in more detail. So that's our sign convention. You need to sort of get used to it. And some people use a slightly different sign convention, so this is not set in stone like the shear and bending moment diagrams are. But you can work with either sign convention, and basically you'll get the same result as long as you're consistent with what your sign convention is. So what we're going to do is we will draw the circle, and what we know is that the coordinates of every point on the circle works in our solution equation. So that's the idea behind it. This is the equation of a circle, and any point on the circle, so that means what? Any point on this circle will make this equation be true. So that we have to keep in mind. So we're going to be interested in a lot of different points on the circle, not just one point usually. So, okay, so I'm going to show the method, and in this example, which says draw the Mohr circle for this stress condition. So now, this is the way everybody does it. Now notice, these, everybody just draws one arrow. It's a little bit confusing for students because normally when we draw stresses, we draw lots of arrows. So look at, when we get back to the original, the way that I did this, which is like that. We draw lots of arrows. Lots of arrows means stresses, because that's just the way things, we always do things. We always draw lots of arrows. But strangely, for these problems, people don't do that. Instead, they just show one arrow means stress. Normally, one arrow means force. So just be aware that it's a one arrow, but it's a stress. It's the way everybody does it. Get used to looking at these. And so I'm just telling you right up front, one arrow means stress. So I'm drawing stresses, but I'm only drawing with one arrow. Okay, so here is my stress condition. And I want to draw the Mohr circle, which means I want to find the center, radius, what we're going to call sigma 1, sigma 3, beta, and tau max. So we're going to get all that information from the circle, and I'll describe it as we go along. So notice that one thing you need to know is that the center of the circle is always on the x-axis. Now, why is that? Well, we know why, because the center is always, the y-coordinate of the center is always 0. So that means that the center is always on the x-axis. The y-coordinate of the center is 0. So that means the center of the circle is always on the x-axis. So you need to know this. Don't draw any circles. If you draw any circles that are not, where the center is not on the x-axis, you're not going to get any credit. I'm not going to give any credit for that. So your circle is always, always, always on the x-axis, and it makes your life easier. In other words, so, once you realize that, you go, okay, can't draw the circle all over the place, and, you're less likely to get the circle wrong. Okay, so here's my stress condition, and I'm going to draw the circle and get these things. So, all right, the first thing that we have to do is recognize the different planes and things. So maybe I'm going to move this down a little bit, because this is really part of the solution here. So I'm going to move that down. Okay, so remember there's our sign convention right there. For sigma, tension is positive. For tau, counterclockwise about the center is positive. So I'll show you what I mean by that. So let's take a look at the stress situation that we have here, and let's draw the points that we know. So in other words, we have a sigma and a tau on this vertical plane here. Let's do that one more time. Notice this is a vertical plane. This is a vertical plane. This is where people get messed up. I know you know what a vertical plane is, but strangely enough, people mess this up. Okay, so when they start looking at this, they get confused. But just think back. That's a vertical plane. You know that this is a horizontal plane. You know that this is a horizontal plane. So don't mess that up. You know what it is. Just recognize it. That we're talking about the planes that we're acting on. And if we characterize what our stress situation is, well, I can make a little table here. There's one way to do it. And what do I see? Well, I see that I'm going to look at this plane. That's the vertical plane. So I'm going to write down vertical plane. And I'm going to look at the stresses on that plane. The first thing I see is I see a sigma that is 8. Now it's tension. Tension is positive, so that's what? That's positive 8 on the vertical plane. So I'm going to write that down. And then I have my tau, which, the tau is equal everywhere. So on every single plane, the tau is equal. So once we determine that, so the tau is everywhere 3 psf. We just have to get the sign right and the sign says, the sign convention that we're using is counterclockwise about the center of the square is positive. So what do I mean by that? Well, if I take a point at the center of the square and on this vertical plane, what does that mean? Oh, it's going like that, counterclockwise. Counterclockwise is positive, so it's a positive 3. So I have, for my sigma, I have positive 8. My tau, I have positive 3. So got this down. Now, let's look at the horizontal plane. So I look at this horizontal plane. Now, it doesn't matter. I could look at this plane, that horizontal plane. It doesn't matter which horizontal plane because, as I said, there is redundant information here. So you can look at either of those horizontal planes, and then when you're doing the vertical plane, it doesn't matter which vertical plane you choose. You're going to get the same answer. In other words, if I look over here, what do I see? That's still tension, positive 8 on my vertical plane, and that's still counterclockwise, positive 3. So it doesn't matter which vertical plane I look at to make my little table here. So then I look at my horizontal plane, and what do I see? That's still tension. It's going down. Remember, it doesn't matter that it's going down. Tension goes away from the body. So that is going to be a positive 2. So on my horizontal plane, I have positive 2 for that sigma. And now I've got this tau. Well, that's clockwise about the center, right? It's clockwise. So that's going to be negative. So I have a negative 3 for my tau. Again, I could have used this plane up here. That is tension. So it's still positive 2 away from the body. And this is still clockwise. So, it goes like that. So I still get a negative 3 there. So, and when you're making this table, one will be positive and one will be negative. I mean, it could be, So there's always going to have one positive, one negative. So just to let you know. So if you get them both with the same sign, something went wrong. Okay, so now I have my little table, and it's important to pay attention to the vertical plane and horizontal plane as we do this. It's going to be important later. So that means what? So now that I have my table made, well, I can make my points. So the sigma is x, tau is y. The sigma is x, tau is y. So now what I want to do is I now want to plot these points. So where people make mistakes is they put sigma on the y. They put tau on the x. Don't do that. Sigma is x, tau is y. And I'm going to make my plot here. So I draw it like this. I have sigma theta. We call it sigma theta, tau theta. And I'm going to plot one point, vertical plane 8, 3. So I come along here and draw it to scale. It helps a little bit. Approximately to scale. Doesn't have to be exact. I put 8, 3. And then I have to write, you really need to write this, 8, 3, that's the stress on the vertical plane. Okay, so we've written it right like that. 8, 3 on the vertical plane. This is 2, negative 3 on the horizontal plane. So I come over 2, down 3, 2, negative 3 on the horizontal plane. You need to write the horizontal plane for important reasons later. So I now have 2 points on my Mohr circle. What do? Well, I draw a straight line between them, and there's my center. It's very straightforward. If you see the way I could go back to this equation And you could see how to do that, but you know, it's not worth it. I'm just going to tell you how it works. It does it like this. And so I have, my 2 points here. Or sorry, 2 points here, and then I draw a line between them and I connect them. And that gives me the location of the center. So how do I get that center? Like I said, this problem, you don't have to do a lot of complex math to solve these. It's all basic geometry and trigonometry. So I know that the center is on the x-axis. So what do? I just simply split the x-coordinates to get the x location. I know that the y location is 0, or 0. So my x-coordinate here is 8. My x-coordinate there is 2. Well, I take the average of those to get the center. 8 plus 2 over 2, which is 5. Okay, so I get my location of my center simply by finding the average of the 2 x-coordinates. And there it is, 5, 0. Once I have that, I'm going to create this little triangle here, and I'm going to find the hypotenuse of that triangle, because the hypotenuse of that triangle is the radius. So if I know this is 5, and over here I'm at 8, well, that means that distance is 3. So I'm able to get that leg of this triangle, and then the y-coordinate is 3, so this is going to be 3. So to get the hypotenuse of that triangle, I simply take the square root of 3 squared plus 3 squared. It's the Pythagorean theorem. You've all done it. So I get a radius of 4.24. Once I have that, then I can get a lot of information from this. I'm going to call this point over here on the x-axis sigma 1. I'm going to call this point over here sigma 3. So it's also going to be on the x-axis. So also called the major principal stress, minor principal stress. And what's the value of sigma 1? Well, it's the center plus this distance, which is the radius. So the center plus the radius gives me sigma 1. So sigma 1 is the center plus the radius. Sigma 3 is the center minus the radius, because your number line, you're going the other way. So like I say, sigma 1 is the major principal stress, sigma 3 is the minor principal stress. And so I just take the center is 5 plus the radius. I get 9.24 for my sigma 1. And my sigma 3 is the 5 minus 4.24, 0.76. And I'm also interested in this point tau max. Tau max is simply the radius. So tau max is the radius. It's always this way. So it's this straightforward. The other thing that we need is this angle beta that's going to help us solve more complicated problems. And so you can see that beta is the arctangent of 3 over 3. So beta is the arctangent of 3 over 3, and beta is 45 degrees. Every problem is different. We're not going to get 45 degrees for this in most cases. So that gives us all of the information that we have that we want to get us going in the problem. We now are able to draw the circle. Now, remember, every single point on this circle represents a stress on some plane. I don't know which plane right now, but there's, if I look at it, so all these different planes here, so, the full spectrum of planes at 20 degrees, at 30 degrees, at 45 degrees, at 60 degrees, at 62.5 degrees, every single plane, stresses on every single plane is represented on this circle. In other words, if I look at, I don't know what this point is, but that point looks like about, x equals, well, let's see, x equals 2.5, y equals 2.5, for instance. No, it can't be that because that's, never mind. X equals, well, I haven't drawn this, but no matter. The coordinates of that particular point, whatever they are, they represent the stresses on some plane. I don't know what plane they are, but the coordinates of that point gives us a sigma and tau for some plane. So that means that if I look at this, what do I see? Well, that stress is 9.24 PSF. Well, what does that mean? That means that there is some plane in here that has a stress, a tensile stress of 9.24 PSF. Now, what do I know? If things are going to crack, for instance, they're going to crack with a large tensile stress. And that is the largest one. So if it's going to crack, assuming a homogeneous and isotropic material, we are going to get cracking on the plane on which this stress acts. So we're going to try to figure out what plane that is. I know the tensile stress. If this tensile stress exceeds the tensile strength of the material, then we are going to get cracking on that plane. For instance, if it's brittle, cracking failure, something, what I mean? It goes into other details. But no matter, we are going to want to know what plane has the greatest tensile stress on it. So, all right. All right, I'll stop there.